Have you ever wondered if there's like one simple, universal rule that explains how things move? I mean, everything from a thrown ball to a planet zipping around the sun. Well, it turns out there is. So let's dive into this master code of motion.
All right, so take a look at these two. On the one hand, you've got this sleek Formula One race car, literally designed for one thing, insane speed. And on the other, a massive transport truck, built for just raw power. Now, both of these have incredibly powerful engines, but they behave in totally different ways out on the road.
So, what's the hidden principle here? I mean, why does one just fly off the starting line while the other takes its sweet time building up speed? It's not just about having a big engine, not at all. The secret is a single, super simple rule that governs, well, everything that moves.
Okay, let's start by digging into the mystery of that race car. Understanding this, well, that's going to be our first step to unlocking the universal rule of motion.
It all comes down to this dance between three things. First, how much stuff an object is made of. That's its mass. Second, how hard it's being pushed or pulled. That's the force. And third, how quickly its speed changes. That's its acceleration. See, the race car, it has a tiny mass, but a huge force from its engine. And that combo gives it insane acceleration. Now, the truck also has a huge force, but its mass is just enormous, which means it simply can't change its speed anywhere near as fast. To really get a feel for this, let's simplify it even more. We're going to play a little game of push and pull. Okay, I want you to imagine we're on a perfectly smooth, totally endless sheet of ice. There's zero friction to get in our way. It's just us and a sled. And we're going to see what happens when we give it a push. This is physics at its absolute purest. All right, first up, let's just think about the push itself. If you give that sled a huge shove, it's going to speed up really, really quickly. That's a big acceleration. But if you just give it a gentle little nudge, it'll still speed up, but much more gradually. The takeaway here is super simple. A bigger force creates a bigger acceleration. They are what we call directly proportional. Okay, now let's think about the sled itself. If the sled is empty and light, even a tiny push sends it flying. But what happens if we load it up with heavy boxes? Well, it becomes stubborn. This stubbornness, this resistance to changing its motion, is a property we call inertia. And the way we measure it is with mass. So it's pretty clear. More mass means less acceleration for the exact same push. It really is that simple. So we've got our two key observations, right? More force means more acceleration, and more mass means less acceleration. Now let's see how these two incredibly simple ideas combine to form one of the most important laws in all of science. And here it is, Newton's second law of motion. And what it does is perfectly capture what we just saw with that sled. It states that an object's acceleration is directly proportional to the net force. That's the total combined push or pull acting on it. And at the same time, it's inversely proportional to the object's mass, exactly like how that heavier sled was way harder to get moving. So these relationships are spelled out right here. You can think of it like this. Force and acceleration are directly linked. You increase one, you increase the other. But mass works the other way around. You increase the mass and the acceleration goes down. These two balancing acts are the core building blocks of our universal rule. And when you put those two ideas together, you get this. F net equals ma. Three letters that literally change the world. Force equals mass times acceleration. This is it, the simple, elegant rule that connects force, mass, and motion for pretty much everything in the universe. And check this out. This graph illustrates that relationship brilliantly. If you plot the net force you apply against the acceleration you get, you end up with a perfect straight line. So what does that tell us? Well, it means as one goes up, the other goes up at the exact same rate. And the steepness of that line, what we call the slope, that is the object's mass. A heavier, more massive object would create an even steeper line because you need way more force to get the same amount of acceleration. But now look what happens when you plot acceleration against mass while keeping the force the same. It's not a straight line anymore, is it? It's a curve. And this shows that inverse relationship perfectly. As the mass gets really, really big, the acceleration gets closer and closer to zero. It just becomes incredibly difficult to get it to speed up. All right, theory is great and all, but let's see this law in action. We're going to use F equals ma to solve a real-world problem and see just how powerful it really is.
Okay, so imagine a volleyball serve. We're told the net force is 36 newtons. That's our unit for force. And it's acting on a ball with a mass of 0.24 kilograms. Our goal? Find the volleyball's acceleration. So we just take our rule, F equals ma, and we rearrange it to solve for a. That means acceleration equals the net force divided by the mass. Then we just plug in our numbers, 36 divided by 0.24.
And the answer is 150 meters per second squared. Now, to put that into perspective, that means for every second that force is applied, the ball's speed increases by 150 meters per second. That is an absolutely incredible amount of acceleration, and we calculated it with just one simple formula.
All right, now for the final piece of the puzzle. Let's connect this law of motion to the most famous force of all, gravity.
Okay, I want you to think about any object in free fall. An apple, a dropped pen, whatever. If we just ignore air resistance for a moment, the only force acting on it is gravity. And that means gravity is the net force, so we can use our F equals ma formula to see what happens. And here is where it all connects. We start with our rule, F equals ma. Now, for a falling object, the force F is the force of gravity, which we can call F sub g. And its acceleration a is that very specific acceleration caused by gravity, which scientists just call g. So we just swap the letters. F equals ma becomes F sub g equals mg. The famous formula for an object's weight? It's actually just Newton's second law in disguise. So the crucial point is this. The very same rule that tells you how much force you need to accelerate a race car is the exact same one that describes how an apple falls to the earth. It is truly universal. Which leaves us with a final thought. If this one beautifully simple rule, F equals ma, can explain everything from a volleyball serve to the force of gravity itself, what other secrets of the universe, from the orbit of planets to the collision of entire galaxies, is it just waiting to unlock?